Hi everyone. In our previous lesson we learned counter sets. Today we will start a new chapter, measurable sets, and a subtitle is the measure of a bounded open set. Let's start definition. Definition. The length of open interval AB is called the measure of the interval AB and is denoted by MAB is equal to B minus A. It's clear that for any interval AB, the measure of AB is always greater than 0. The measure AB is always greater than 0. Lemma. So, let's consider that finite or countable number of pairwise disjoint intervals delta 1, delta 2, delta n are contained in the open interval delta, that's the subset of R. Then the sum of the measure of delta cos are less than or equal to measure of delta. Let me show you. Let it be an open interval delta. Okay, and this is pairwise interval delta 1, also the disjoint interval delta 2. Let it be another disjoint interval delta 3, and etc. Let it be delta n, for example. As you know, there are not common elements in these disjoint intervals. So the sum of all the measure of delta k is less than or equal to the measure of our main interval delta. Another definition, the sum of the length of all component intervals of G is called measure of the set G and denoted by Mg. So Mg is equal to the sum of all delta cos, where delta cos are component intervals. Here delta cos were pairwise disjoint intervals, but here they are component intervals. And look through the difference. Here the length is less than or equal to m delta, but here mg is equal to the sum of m delta cos. If G is bounded set, then it's contained on some finite interval delta. Then by above lemma, measure of any bounded and open set G and open set G is finite number. It means that mg is less than infinity. If G is a closed set, then mg, of course, is 0. So, any open and bounded G mg is less than or equal to 0. Sorry, here it's equal, okay? Not non-equal, it is equal. And if G is a subset of delta, then the measure of G is less than or equal to measure of delta. For example, let's consider counter set. The counter set, let it be G0, is in the form of, do you remember? 1/3, 2/3, union 1/9, 2/9, union 7/9, 8/9, union, and etc. So here mg is equal to 1/3 plus 2/9 plus 4/27 and etc. plus 2/n minus 1, 3/n, and this is equal to the sum of 2/n minus 1 or 3/n, and this is equal to 1/2, the sum 2/3 to the n, 1/2 multiply 2/3 over 1 minus 2/3. It was the length of counter set. Do you remember? I'll recall it to you again. And this is equal to 1, as you see. Look through the properties of the counter set. Length. The length formula was that. Okay. Another theorem. Let G1 and G2 be two bounded open sets. If G1 is a subset of G2, then the measure of G1 is less than or equal to measure of G2. Another theorem. If the bounded open set G is the union of a finite or countable family of pairwise disjoint open sets, what it means? It means that they have no any common elements. That is, G is equal to the union of GCAS, and GK1 intersection GK2 is a empty set, a valid set. What does it mean? They don't have common elements. Then the measure of G is equal to the sum of the measure of G case. But our third theorem is a little bit different. If a bounded open set G is the union of finite or countable number of open sets G come that is G is equal to union of G case. Then MG is less than or equal to the union of MG case. What is the difference between these two theorems? Look, both of them is bounded open set G. Both of them is the union of finite or countable sets, but here countable family of pairwise disjoint open set. It means that they has no common element. But here just a number of open sets. It means that they may have common elements. Okay. For example, here the pairwise disjoint sets are, for example, they. Okay, they are disjoint. They have no common elements. But here, GKs are, for example, let it be the first set. Let it be the second set. For example, let it be the third set. You know, they have common elements. So here the length is equal to the sum, but here the sorry, not length, the measure. Here the measure is less than or equal to the union of MGKs. Now we will start to learn the measure of bounded closed set. We have learned the measure of bounded open set. Now let's try it in closed set. So definition: consider that F is a subset of R. F is from R. It is non-empty bounded closed set, and S is the smallest segment, which means closed interval, which contains F. Then the numbers MF is equal to B minus A minus CSF is measure of F. Here, what is CSF? Do you remember what is CSF? Let's recall what's CSF. For arbitrary sets A and B, if B is a subset of A, then the difference of AB is called component set of B with respect to A and denoted by CAB. And here it's clear that S minus F is called the component of the set F with respect to S. Okay? Examples. Let's consider that F is a closed set AB. If S is AB, and what's the component of F with respect to S? Of course, it is empty set. So the measure of AB, it means the measure of any closed intervals, is equal to B minus A minus measure of closed set, and this is equal to B minus A. It means that the measure of a closed interval is equal to its length, B minus A. Another example. This is our first example. Let's consider another example. Okay, let F be the union of closed interval AK, BK, and here AK and BK's are pairwise disjoint closed intervals. What does it mean? It means that they have no common elements. Consider that this is another consideration. BK is less than AK plus 1, where K is equal to 1, 2, and N minus 1. What does it mean? Let's consider our set, pairwise disjoint sets, is A1, B1. Let it be here. A2, B2. This. A3, B3. And etc. It keeps going. For example, AK, BK. Here is AK plus 1, BK plus 1. Pay attention, please. This property is satisfied. So BK is less than AK plus 1 everywhere. B2 is less than A3, B1 is less than A2, and etc. And it keeps going, so till here, AN and BN. Okay? It's clear that S is equal to A1 and BN. And the component of F with respect to S is equal to, look please, let me show you the union of these intervals. Okay? These intervals are B1, A2, B2, A3, Bn minus 1, An. Then the measure of F would be Bn minus A1, okay? And minus the union of AK plus 1 minus BK. what do is equal bn minus a1, yes, and minus a2 minus b1, a3 minus b2. It keeps going and it's equal to b1 minus a1 plus b2 minus a2 plus bn minus an, and the length is equal to a1 b1. Okay, this is a1 b1 plus the measure of a2 b2 plus, it keeps going, the measure of an bn. So this is our another example, and we obtained that the measure of a finite number of pairwise disjoint closed intervals is equal to the sum of the lengths of these intervals. Yes, the lengths of these intervals. Look at our third example. Let's consider Cantor's perfect set. What does it mean? It means that our set S is a unique set 0, 1, and the component of F with respect to S is G0, which is Cantor's open set. We have found that in our previous lessons, the m of the measure of G0 is equal to 1. So the measure of P0, Cantor's perfect set, is equal to 1 minus 0 minus the measure of G0. Yes, measure of G0, and it's equal to 0. So the Cantor's perfect set P0 has measure 0. This is our first theorem about bounded closed set. The measure of bounded closed set F is a non-negative number. Try to prove it yourself, okay? And write below in the comments if you have any question, please. Let's write lemma. If bounded closed set F is contained in the interval delta, which is equal to AB, then the measure of F is equal to measure of delta minus measure of the component of F with respect to delta. Let's consider, let it be our interval A and B. This is delta. And let it be our closed set F. Then the measure of F is equal to the measure of delta B minus A minus the component of F with respect to delta, the measure of the component of S with respect to delta, what is the component? The components are these intervals, yes? Here is our second theorem. If f1 and f2 is two closed bounded sets, and if f1 is a subset of f2, then the measure of f1 is always less than or equal to the measure of f2.